Hello everyone, I'm Jacob Czakareski, and on behalf of our team, I will present our work that contributes a dataset and modeling of rate-distortion characteristics and head movement navigation for full ultra-high definition 360-degree video. We gratefully acknowledge the support of our sponsors. Our contributions are: we collect and investigate rate distortion and navigation characteristics of full ultra-high definition, that is 8K 360-degree videos. And these attributes can provide valuable insights in resource performance trade-offs and VR navigation for such content. We also formulate statistical navigation model and space-time 360-degree video tile rate distortion models. And finally, we investigate key use cases of the developed data and modeling in streaming, content distribution, and 360 perception and saliency. Motivation for our work. Virtual reality is an emerging technology that has the potential to broadly impact and advance our society. In conjunction with 360-degree video, it can enable remote scene immersion to help advance education and training, telepresence, healthcare, etc. Presently, only low quality, low resolution, low frame rate 360-degree videos are commonly available. And this is in stark contrast to the expectations for next generation high quality immersion that should comprise a 360-degree panorama of 12K spatial resolution and frame rate of 100 frames per second, among others, as envisioned by MPEG. Thus, full UHD 360 video represents one natural and relevant advance towards the anticipated next generation VR immersion. And understanding its rate distortion and navigation attributes can advance immersion quality and resource allocation in VR systems. 360 video enables a 360-degree look around of a remote scene for a VR user. A typical 360 video setup comprises an omnidirectional camera that captures the content. The raw spherical data is then mapped to an equirectangular panorama for more efficient compression. Then, on demand, the compressed content is streamed to a VR user over a network of typical limited bandwidth capacity C. The user at any point of time can only experience a small portion of the entire 360 panorama on his headset. Viewport adaptive streaming has been explored recently to overcome the inefficiencies of monolithic 360 delivery that transmits the entire panorama to the user all the time. This is unnecessary, and presently, given the capabilities of existing network, it is not even feasible to stream the entire panorama in high quality. Hence, viewport prediction and effective resource allocation are key for VR system optimization, and therefore having user navigation and rate distortion datasets and models for full ultra-high definition content is critical to advance these objectives. With respect to related work, there have been several studies that have contributed navigation datasets and capture software, or have examined the rate distortion dependency of 360 video in a few different contexts. However, they only considered low quality 4K 360 videos due to their wide availability. Therefore, there is a state-of-the-art gap that our paper fills by contributing datasets and modeling of rate distortion and head movement attributes of tiled, full ultra-high definition 360 videos. This can be very impactful on the road to next-generation immersive media systems. We developed our dataset and modeling using 15 raw 8K 360 sequences that we make available online through our paper. 9 stem from Shanghai Jiaotong University, 2 stem from GoPro, and 4 stem from InterDigital. Their basic characteristics are shown here on the slide, and they are described in more detail in the paper. They represent diverse content and use cases, where the Shanghai Jiaotong and InterDigital sequences are mostly static and they have multiple moving background objects with no distinct foreground object. And therefore they lead to diverse VR navigation across different users, and also they exhibit slowly varying rate distortion attributes because of this nature. On the other hand, the GoPro sequences are much more dynamic and they have a primary moving object. Therefore, they lead to higher VR navigation correlation across users, and similarly, because of their nature, they exhibit higher temporal dynamics of their rate distortion attributes. We compress each sequence using AGVC and 8x8 tiling layout. where each GOP tile is compressed independently. We progressively increase the quantization parameter for each encoding, so that we provide a well-sampled range of video quality values from low to high. We used Oculus Rift and the WirdlyGeek player to enable a user to navigate the compressed 360 videos on a VR headset during a head movement recording session. We used the OpenTrack software to record the navigation actions of the user, where precisely we capture the yaw, pitch and roll head rotation angles that uniquely describe the head orientation of a user for every 360 video frame displayed on the headset. We also captured user demographics information and we include it in the paper. During a recording session, there is an attending researcher that leads the session and assists the user and monitors his or her behavior. Test sequence is initially shown to familiarize the user and adjust the setup prospectively. And the user is asked for discomfort after each playback, and the session is terminated if simulator sickness is observed. Our contributed dataset comprises 5 multi-dimensional structure arrays in MATLAB. In particular, array 1 comprises the yaw, pitch and roll angle for each video frame J across every user and 360-degree video pair. Then the other 2 arrays, array 2 and 3, comprise the rate and distortion value, respectively, for all 64 tiles in each GOP for every 360 video and QP value pair. And finally, array 5 and array 4 and array 5 comprise for each 360 video the exponential and power law Rate-Distortion models for all 64 tiles in each GOP that we contribute. We carry out brief head navigation analysis here. We examine the CDF of yaw, pitch and roll for 2 representative sequences. We can observe that yaw has a broader variation, and that is due first to the doubled measurement range used to capture this rotation angle. However, that is also due to our natural tendencies to navigate by rotating our body and head left to right. On the other hand, we observe a very low variation of pitch, meaning that the users exhibit only minimal head tilting up and down. So these 2 last characteristics lead to the observation that therefore equatorial regions are much more popular to navigate for the users than polar regions of the content. And finally, if you compare the CDF of yaw for the 2 sequences, we can see that in the case of runner, the users navigate all angles evenly. On the other hand, for basketball, we can observe that the users focus in their navigation on a few representative angles. We use the navigation data to formulate a navigation likelihood model as follows. First, for every tile NM and video frame J, we formulate the set S that captures the pixel overlap between the tile and the user viewport at that time instance. To account for the unequal shape and size of the viewport depending on its latitude on the panorama, we then normalize these quantities leading into weights WJ for every tile. Finally, we formulate the likelihood that the tile is navigated by the user during a given time period by summing up its respective weights and dividing by the number of frames present in that time period, as shown here. For our Rate-Distortion analysis, we empirically selected the QP range 15 to 35 and measured the encoding rate and mean square error distortion for each GOP tile and QP value used. We compare the encoding bitrate and distortion across the 2 cases of QP is equal to 20 and 35 for the entire video corpus. We observed in terms of bitrate a ratio of 10 to 20 times between the 2 cases. For the case of QP is equal to 20, we observed a smoother tile distortion distribution, which means a good visual quality is achieved across the entire video corpus. For the case of QP is equal to 35, we observe higher tile distortion average and variance values as expected. We examined the encoding bitrate and distortion across the GOP tiles for the 2 quality cases for the sequence runner as a good representative example. One overarching conclusion is that the impact of the content complexity is critical, and therefore this motivates the use of unequal QP values across the 360-degree panorama for optimized performance. We explore two dependencies in the empirical data: tile bitrate versus tile distortion and tile bitrate versus quantization parameter QP. And then we use two models to fit the data: exponential and power law. We explore the accuracy of each model in the paper, where we provide a comprehensive assessment in terms of absolute and relative prediction error across the entire video corpus. To examine the accuracy of the QPR dependency modeling, we present three graphs indicating the empirical and model predicted values for three representative tiles of the runner sequence. These tiles are selected to cover the entire range of QPR values observed across our video corpus, as indicated here. We can observe that the exponential model fits the data much more accurately. There are occasional small differences between the empirical and the model data. However, they are observed infrequently, and they are certainly negligible relative to the power law model. We also examine the cumulative distribution function of the relative prediction error across the two models and the two QP values that we studied before for three representative sequences now: runner, basketball, and gate night. These graphs are included in the right-hand side of this slide. We can observe that again the exponential power law models perform very distinctly, where 2 out of 3 CDF graphs for the power law model and QP is equal to 35 lie outside the considered x-axis range. Interestingly, we observe very similar trends with distinct QPR values across all videos examined for the exponential model. Similarly, we next examine the accuracy of the Rate-Distortion dependency modeling, where again we present three graphs showing the empirical and model predicted values for the same three tiles of the runner sequence. In this case, we can observe that the power law model has a smaller error margin, where the power law model exhibits low accuracy in the case of tile 5 and high accuracy for tile 38 and 27. This is expected in the case of tile 5 because the distortion and bitrate values are very small and it's very hard to fit them with a model. We also know that we observe slightly lower accuracy for tile 27 because of the much higher rate distortion range that the model needs to cover in this case. And again, we also include a graph that shows the cumulative distribution function of the relative prediction error of both models for the two QP cases considered and the three sequences that we considered earlier. And we can see that now we observe a reverse behavior where the power law model is consistently more accurate. And similarly, we observe opposite trend with respect to the QP values across all models and videos. That is, the relative prediction error exhibits smaller and steeper CDF functions for QP is equal to 35. And finally, we observe higher divergence among the three graphs for the exponential model and QP is equal to 20. There are multiple key use cases of the developed dataset modeling. First, in streaming system, we can optimize the rate allocation, aiming to maximize the delivered viewport quality using the formulation shown here, enabled by our navigation likelihoods and rate distortion modeling. This is convex optimization, therefore it means it will have fast and global solution. Similarly, in HTTP2 push methods, we can use the navigation likelihoods PIJ to accurately predict the next GeoPip tiles to send to a client. In neural adaptive streaming that leverage deep learning to construct a super resolution of a 360-degree video which is received at low quality at a client, we can use similarly the navigation likelihoods to anticipate the client's behavior and allocate the remaining bandwidth so that we minimize the residual error after super resolution. And in general, our datasets can benefit training, simulation, and improvement of such neural approaches. Yet, in distribution systems that integrate caching and transcoding, our dataset and modeling can contribute to caching, prefetching, and component interoperability in such systems. In particular, we can use the navigation likelihood to prefetch to the caches highly popular tiles that are demanded by the user. Then we can use the RD modeling and rate allocation analysis to transcode these tiles at the caches to minimize the delivery of viewport distortion to the clients. And these advances can simultaneously make impact on system scalability. where in particular, instead of carrying a central operation of the server for all clients, dynamic encoding can be carried out at the caches for a subset of the clients. RD modeling can also benefit our RD modeling can also benefit the Dutch methods, where we can predict the transmission capacity in the next time instance and use our analysis to determine the optimal coding rate for the tiles requested in the next GOP segment. Finally, in studies of immersion perception and saliency, our dataset and modeling can be used to advance the perceptual interaction and quality of experience in immersive environments. In particular, they can facilitate understanding of the viewing behavior of full ultra-high definition 360-degree content. They can also help develop related behavioral models of viewing navigation and fixation points. Similarly, they can help identify the salient aspects of the content to explore saliency prediction methods and to benefit applications such as 360 video synopsis, compression, and streaming. In conclusion, we recorded and studied Rate-Distortion navigation characteristics of full UHD 360 videos. They can provide valuable insights in resource performance trade-offs and VR navigation. We developed related statistical navigation and Rate-Distortion models, and we studied key use cases in streaming, content distribution, and 360 perception and saliency. We highlight again that understanding these characteristics can make strong impact on the road to next generation immersive media.